everyone, and welcome. To all the infrastructure admins out there, consider this your in-depth explainer module directly targeting the NCP-MCI 7.5 certification, specifically Section 4.1, Capacity Optimization Techniques. Whether you're actively cramming for test day right now, or you're just looking to tighten up your Nutanix AOS 7.5 environments, you are definitely in the right place. We're going to dive right in and make absolutely sure you have this foundational knowledge completely locked down. Here is our roadmap for the next 10 minutes. We'll quickly cover why optimization matters, compression and deduplication, erasure coding and tiering, concrete optimization examples, common exam traps, and we'll wrap up with the key facts to memorize. All right, let's get started with Section 1, Why Optimization Matters. So at the architectural level, Nutanix capacity optimization essentially rests on 4 core pillars. You've got compression, deduplication, erasure coding, which we usually just call EC, and intelligent tiering. Why do we even use them? Well, ultimately, it's to drastically reduce your physical storage footprint and improve your overall I/O bandwidth. But before we get into the weeds of how they do that, you really need to grasp 2 overarching concepts that define how these pillars operate. The first is ILM, or Information Lifecycle Management. Think of ILM as the brain of the operation. It constantly monitors access patterns and defines your data's temperature, meaning is this data hot and frequently accessed, or is it cold and just sitting there? The second concept is RF, or replication factor, which dictates exactly how many copies of your data are maintained across the cluster for fault tolerance. Keep ILM and RF on the back of your mind as we go through this. Moving right along to Section 2, Compression and Deduplication. Now, what's really fascinating here is how AOS intelligently handles data based on your specific configuration. There are 2 main types of compression you have to understand for the exam. On the inline side, when you create a brand new storage container, this is enabled by default across all license tiers. It compresses data immediately as it's written. Because it happens instantly, it inherently has a delay of 0. On the other side, we have post-process compression. Just like the name implies, this compresses data after it's already been written to the disk, completely delaying that processing overhead until a more optimal time for the system. And speaking of that delay, I need you to burn this golden number into your brain: 60. For post-process compression, Nutanix explicitly recommends setting a delay of exactly 60 minutes. This gives the system a full, uninterrupted hour after the initial write operation before it starts doing the heavy lifting of compressing that data. You absolutely must remember this for the test. If a scenario asks you for the recommended delay for post-process compression, the answer is always 60 minutes. Okay, let's talk deduplication, which is all about eliminating those duplicate data blocks. You have to clearly distinguish between the 2 distinct flavors here. First, there's performance tier deduplication. This one works inline, right within the content cache. Its main job? Reducing the footprint of your application's active working set, your hot data. In contrast, capacity deduplication works post-process. It scans your persistent, cull data that's just sitting on your hard disk drives, and it strips out repetitive data to increase your overall effective storage capacity. So remember the rule of thumb. Performance tier is inline for the cache, and capacity is post-process for those persistent HDDs. Let's jump into Section 3, Erasure coding and tiering. For the exam, you really need to memorize these strict node minimums for erasure coding. EC has very specific requirements depending on your replication factor. If your cluster is set up for node 1n/1d fault tolerance, which equates to replication factor 2, you need a strict minimum of 4 nodes to even support erasure coding. If you're using node 2n/2d, which is replication factor 3, that requirement jumps up to a minimum of 6 nodes. Do not mix these up on test day, guys. RF2 needs 4 nodes, RF3 needs 6. Simple as that. And this brilliantly illustrates why EC is heavily tested. Take a look at the usable capacity compared to the state after erasure coding is applied. Instead of just fully replicating data blocks to achieve fault tolerance, which honestly eats up massive amounts of space, erasure coding takes a strip of data blocks across different nodes and calculates parity. If a node fails, it just uses that parity to rebuild the missing blocks. The result? You can literally increase your usable capacity by up to 75%. It's a massive, massive efficiency gain, saving physical space while keeping your resiliency high. Meanwhile, let's look at intelligent tiering and how it dynamically manages all this across your drives. It's basically a 3-step dance. Step 1, that information lifecycle management we talked about, ILM, continuously monitors access patterns to figure out the data's temperature. Step 2, the hot, frequently accessed data is kept right on tier 0. That's your highest performing, low latency flash tier, like PCIe NVMe or SATA SSDs. Step 3, when that data goes cold, meaning nobody's touched it in a while, ILM physically migrates it down to Tier 1, which consists of your high-capacity, higher latency DAS SATA hard disk drives. And if that cold data is suddenly needed again, boom, it gets promoted right back up to the flash tier. Up next, Section 4, Concrete Optimization Examples. To make sure this really sticks, let's examine how NEOS actually calculates EC strip sizes out in the wild. The maximum supported and recommended strip sizes are usually 4 data blocks to 1 parity block, or 4 to 2. Now, the absolutely crucial point regarding strip sizing is the trade-off. Wider strips will absolutely give you more space savings. However, they significantly increase the cost of a rebuild if a node drops offline. Rebuilding data requires heavy read operations, so during a rebuild, it will noticeably impact your read performance. The wider the strip, the heavier the penalty during recovery. Here's another key metric you just have to know. 7. Erasure coding is an asynchronous background process, and it only touches data that has become cold. Why? To avoid wasting precious CPU cycles on data that's just going to get actively overwritten anyway. The default window for erasure coding to consider write data as cold is exactly 7 days. Keep in mind, EC is actually pretty terrible for overwrite-heavy workloads, which is exactly why this 7-day buffer is baked into the system. Now, here's a very specific edge case scenario that is prime exam material: an all-flash cluster using erasure coding. If you're running EC on an all-flash cluster that includes storage-heavy nodes, you have to architect for optimum performance by adding replication factor +1 storage-heavy or storage-only nodes. So as an example, if you have a 4-node cluster running RF2, you have to add a minimum of 3 storage-heavy nodes. That's your RF of 2 + 1 equaling 3. Don't let them trick you with that math on the test.
Okay, pay attention to Section 5 Common Exam Traps.
Listen up, because this is where a lot of admins lose super easy points. Watch out for these strict limitations. First, if your cluster's metadata usage spikes too high, inline compression is just going to automatically shut itself off and throw an alert. Second, you absolutely cannot use deduplication on a storage container configured with replication factor 1. No way, not an option. Third, if you even want to enable capacity dedupe, Nutanix strictly requires your controller VMs, your CVMs, to have at least 32 gigs of RAM and a 300 gigabyte SSD for the metadata disk. Actually, if you see a question where the CVM only has, say, 24 gigs of RAM, you know right away capacity dedupe is off the table. And finally, like we said, do not enable EC for overwrite-heavy workloads.
Finally, Section 6, Key Facts to Memorize. Let's build your perfect mental cheat sheet right here. These are the non-negotiables. The recommended post-process compression delay, 60 minutes. Erasure coding node minimums, 4 nodes for RF2 and 6 nodes for RF3. The default write cold window for EC, 7 days. To turn on capacity deduplication, your CVM needs 32 gigs of RAM and a 300 gig SSD. And one last fact for you. Because these are asynchronous background processes, calculating and displaying your actual space savings in the UI requires a minimum of 2 full curator scans. If you memorize these exact metrics, you are 100% ready to ace the capacity optimization section of your NCP-MCI exam. But before we go, ask yourself this. As SSD capacities continue to explode and NVMe becomes the absolute standard, will legacy hard disk drive tiering eventually disappear from these architectures entirely? Or will cold data always need a cheap spinning place to sleep? Think about that as you continue your studies. Good luck out there and keep learning.